Okay, so this time we're going to look at those kinematic formulas again, or at least two of them, through calculus. Why do I want to do this? No, you don't have to learn calculus, okay? But a simple formula like the acceleration or velocity formula, acceleration by definition is a rate of change of velocity. So this formula makes plenty of sense to just about everybody. You have a change in velocity divided by a change in time. A rate is just the rate at which something changes, so that makes sense. This mathematically should make sense to you through all the concepts. But then I start throwing out all these other formulas, 1 through 4, and they can seem kind of crazy. So where did they come from? And I showed you where we can derive this down using a graph to get the first formula. But I want to show you there's another way to do it, and if I prove that that way works, it should help prove that calculus can be used for the second way to get the second formula too. So let's go ahead and derive that very first formula that we had, which really is the most basic one we could do from a graph. First thing we're going to do is we're going to say, okay, I'm going to start with this base formula where I have acceleration is equal to that change in velocity over a change in time. Now, what you need to realize is I can go ahead and define how small of a time and how small of a velocity. And when I'm working with calculus, you want to use infinitesimally small. So I'm going to say it's super, super small. And when we do that, we get it to something that works a little bit better in calculus. And so we're going to say that we're getting this tiny bit of velocity and an infinitesimally tiny bit of time. So it's still the same formula, we're just writing it a little bit different. We also need to make some assumptions. So I said these only work for constant acceleration, so we have to say that A is always going to be a constant, okay? The other thing is this little symbol t of naught or t of 0 or t initial, even if you want to do that, we have to say that we're starting with 0 seconds. Why? Because it makes it easier that your time's always going to be nice and simple to figure out, okay? So we'll make these two assumptions and we can derive everything else that we need. The next thing is probably something, if you took calculus, you're not very familiar with. We're just going to algebraically move sides so that I get a new formula. I now get A of dt is equal to dv. I know, in calculus they don't like letting you do that, but we can do it because we understand what all of this is: an infinitesimally bit of time, an infinitesimally bit of velocity, and an acceleration. And so all we did was we multiplied both sides by an infinitesimally small amount of time. Now that we have that, we can do an integral. So I'm going to go ahead and draw my integral sign. And for this one, I'm going to take it from time of 0, or naught time, to some time in the future. Of this one over here, I'm going to take it from my velocity initial to my velocity final. Okay? So this is two calculus integrals. And that's going to equal, when we start working that out, because acceleration is a constant, you actually end up pulling this out of the integral and you just work with the time because that's what it's across anyway. That's one of the benefits of making it a constant. So when I do that, I now have that A is equal to times time that has to be spread across t naught to t. And that's going to equal a velocity that is across v initial to v final. Simple enough so far, right? All right, so then you just work that out because all of those symbols end up just meaning this. I now have acceleration being multiplied t minus t naught, and it's equal to v final minus v initial. And here's the beautiful thing though. Since we know that t naught is equal to 0, thanks to our assumption, we know that this is just t. And what we get is we get that acceleration times time is equal to velocity final minus velocity initial, right? And then it's just a matter of algebraically solving it now, and I get that initial formula, which we can write as v final is equal to v initial plus acceleration times time. And that's the calculus way of solving that exact same thing. I will go ahead and say that remember that our designator here for velocity final, a lot of people will just write velocity at this point because you have a starting velocity and then you're going to find a velocity, so they don't bother with the f. I do that just so that we can keep an understanding that this is what we would find in the end for when we're doing a cross like that. Some people would just write it as v naught to v, same as I did t naught to t, but we write it a little bit differently, and you'll see it in all kinds of different ways too. Now let's look at that second kinematics formula. So I just made our stuff over here small, and then I'm actually going to start this one with our original velocity formula. So we have velocity is equal to a change in displacement over a change in time. And I'm going to do the same thing that I did before, where I said this equals an infinitesimally small displacement over an infinitesimally small time. Okay? I can then do my mathematical wizardry there and get that this is going to equal a velocity times an infinitesimally small time is equal to an infinitesimally small displacement. I'm then going to make my integrals, right? I need to put that across something, so this is t naught to t, and this is going to be just my d initial to my d final. But then I'm going to make a substitution, something that's a little bit odd if you've taken calculus. What I'm going to do is I'm going to take this formula for v, and I'm going to put it over here for that, because I know that v equals that in real life. Because of that, I can plug it in, and now I have a, which is a constant, which is something that I needed, and it's still across time, and so I don't have to worry about quite as much, and I can get a whole different formula. With doing that, I now end up with still going to be across t naught to t, but I'm going to have that velocity initial plus acceleration of time, and all multiplied by an infinitesimally small bit of time is equal to, we still have our infinitesimally small displacement from d initial to d final. And this is where you actually have to know something of integral calculus, because this is how you actually solve it. Luckily, I can go ahead and say that it's not super difficult if you know what you're doing. That v initial gets multiplied by time, and then we add that to our constant, stays the same, but this time goes to the second power, and it's all divided by 2. And that's still across t naught to to, but that's how we would solve for the infinitesimally small part in our integral. And then the other part is real simple. It's just d, which is going to be across displacement final and displacement initial. So displacement initial to displacement final. We're almost there. Our final step here, well, our second to final step, is now we have to move it across those things, so we get VIT plus 1/2 instead of dividing all of it there, times acceleration times time squared minus VI times t naught plus 1/2 acceleration times time squared of time naught. But look, we're in luck because we know that even after we'll finish writing this, d final minus d initial. We know that all of this, TO, is equal to 0. So that cancels out all of that term, right? Because it cancels out all of that term, I can then just algebraically rewrite this as d final is equal to d initial plus velocity initial times time plus 1/2 of acceleration times time squared. And you should have your second kinematics formula. So it didn't come out of nowhere. It's just been derived through calculus. And that's true for all 4 of them. You just need to know this. You don't have to be able to repeat it.